In this video, I just wanted to take some time to discuss the differences between opened versus closed, bounded and unbounded sets, in case that's just really not something that you're very comfortable working with. So I was going to draw some pictures and just show some examples of that and kind of help you figure out different ways to identify those. So I'm going to make just kind of like a table here to help us sort these ideas. So do something kind of like that. All right, so this column here is going to represent closed sets, and this column here can represent open sets. This row will represent bounded sets, and a lot of times you'll see me abbreviate the word bounded with just like BDD or something like that, which I'm going to do here. This row here is going to represent the notion of an unbounded set. Okay, so when a set is closed, the way that we think about this is that it includes all of its edges. And this idea of it having all of the edges is really important. It must have every single one. We say a set is open if it does not include any of its edges, so absolutely none. And we say a set is bounded if it can't really include any sort of like positive or negative infinity. And we can say that a set is unbounded if it could contain either plus or minus infinity. It doesn't have to include both, just one or the other would suffice to make it unbounded. Okay, so let's look at some examples of a set that is, closed and bounded, closed and unbounded, and then open and bounded, and then open and unbounded. So a lot of times a closed set is characterized by having equal signs in it'll be an equality or an inequality. So one example of this would be the region -2 less than or equal to x, which might be less than or equal to +1. And then say on the y, we wanted to put the restriction -3 less than or equal to y less than or equal to 2. If we wanted to draw a picture of this, it would look something kind of like this. So 1 would go here, -1, -2. Okay, so x would be between -2 and 1. So I'm going to have solid lines here because x is between those values. And then we also required that y be between -2 and or -3 and +2. So we'd have solid lines, down there and there. And so x being between -2 and 1 and y being between -3 and +2 means that the area that we're looking at for this particular shape is just going to be what's inside here. Okay, and there's two really key features of this that make it closed and bounded. The fact that it has all of its edges in it, as denoted by the equal signs or the solid lines around it, means that it's closed. And the fact that it is inside, like really well contained inside of a specific shape, means that it is bounded and isn't going to include any sort of like positive or negative infinity or anything like that. Okay. We can have a similar example for it being open, except instead of having equal signs on the inequalities, we'll just do strict inequalities. So we can have -2 is strictly less than x, strictly less than 1, and we'd have -3 strictly less than y, which is strictly less than 2. So if we wanted to draw this one, this time, instead of using solid lines to denote our boundaries or our edges, we're going to use dashed lines at these places, -2, -3 here for y, and then a positive 1 for the other x boundary, and positive 2 for the other y boundary. However, the boundaries themselves are still the same, even if we're not including them. So we are still looking at the inside of this rectangular region here. Okay, so it includes everything inside of the rectangle, but just not the edges of the rectangle. So the inside part makes it a bounded set, and then the not including the edges makes it open. Now, one that's kind of tricky to visualize a lot of times is the notion of a closed but unbounded set. And an example of this would be when we're kind of looking at maybe more of the outside of this rectangle instead of wanting to stay inside of the rectangle. And that could be given by, say we had -2 was actually greater than or equal to x, but then we also wanted to allow x to be greater than or equal to 1. Oops, that should be an x. And we wanted to bound y with -3 being greater than or equal to y. And then we want y to be greater than or equal to 2. So if I were to draw this picture, I'm actually going to wind up with the exact same shape. The only difference is going to be the part of the graph that I shade in. So again, solid lines because we are including our edges this time. But now because we want x to be outside of the -2 and outside of the 1, and the y's to be outside of the -3 and outside of the 2, this region actually represents anything outside of the rectangle. Okay, so it's going to look a little bit more like that. This is unbounded because I can go as far along the x and the y axes, or the x and y axes, as I want to. So it does run off to plus or minus infinity. In this case, it does include both, but that again does not always have to be the case. So it is closed because it includes the edges that are given here because of those equal signs, and also if we want to look at the picture. But it is unbounded because it's really pretty much everything outside of this rectangle, and there's no shape that we could put on here that would contain all of that. We get a really similar picture when we want to look at something that's open and unbounded. We can have the same example, except we drop the equalities. And then my picture would look just like this, dashed lines once again. Like so. But because we want everything on the outside of the rectangle, this is the part that gets shaded in. And this is an unbounded set. But again, it is open because we are not including the edges that are inside of it. So I know that sometimes you see open and closed prior to this point. Bounded versus unbounded a lot of times can be a little bit weird to try to figure out. And just kind of an intuitive way to think about this, although not technically necessarily like rigorous per se, is going to be what happens when you plug in plus or minus infinity for x and y. And if you're able to do that and still have the thing kind of make sense, if you will, as much sense as plugging infinity in can make, if it makes sense, then it's not bounded, and if it doesn't make sense, it's not bounded. So can you plug in, I put quotes around this because you can't really plug in infinity, plus or minus infinity for, and you want to test both with x and y, and have, sometimes you're working with an equality, sometimes you're working with an inequality. If the answer is yes for even one of them, okay, so like you really don't even have to check all of them. So yes for just one, then it is unbounded. So I guess it's a lot easier to notice if it's unbounded. But if it's no for all cases, and when I say all cases, I mean like plugging in plus or minus infinity for x and plus or minus infinity for y, then you have a bounded function because we are never able to allow our set to just kind of run away to infinity. So, I mean, like if we look back over here at our original examples, okay, if I were to plug in negative infinity, say here for x, well, negative infinity is certainly less than or equal to -2. So that would mean that it's unbounded because it is a true statement, I guess, to say that negative infinity is less than or equal to that. So it would be kind of included in that set, if you will. Or you can really include anything in this set. So, but if we go back up here, and if we plugged in either negative infinity or positive infinity, doesn't really matter which one, this would not be a true statement. Same idea over here. We can't get away with plugging anything that's just, I mean, arbitrarily large in this inequality here. So since we're never able to just plug in however large of a number that we want, or plus or minus infinity or what have you, again, I say that you can't really plug in plus or minus infinity, but think about it that way. This is a bounded set because it is all very nicely contained and doesn't ever just kind of run away with however large numbers that we want or small numbers that we want to plug in here. One more thing that I want to mention is the fact that a function, or I keep trying to say the word function, a set does not necessarily have to be open or closed. Open or closed they're not opposites of each other. You can't, it's not like if you don't have one, you have to have the other, or like that they're mutually exclusive or anything like that. It is possible to have a set that is neither open nor closed. So when it's neither open nor closed, what happens is it's going to contain some edges, but not all of the edges. So for example, we could have -2 is less than x, less than or equal to 1, and -3 less than or equal to y, less than 2. If I wanted to graph this, it's still the same shape as what we've been working with, honestly. So -2 would be here, but because this doesn't have the equality, we've got the dashed line, so we're not including this border, which I should probably label -2, -3, 1, and 2. Okay, but this one over here, we are including this boundary. And then similarly here, we do include the boundary for -3, but we don't include that upper boundary there. The area that we are coloring in is still going to be the same kind of inside part right here. So I guess this is a bounded set, but it is neither open nor closed. So just something to kind of be on the lookout for, that it is possible for it to be neither. Fun fact, it is also possible for it to be both open and closed, but you don't really have to worry about that right now. That's not something that we're really going to mess with too much. So, but just so you know, it is possible for it to be both. But for the most part, what you're going to be looking at are open, closed, or neither open nor closed, because that's what's really useful to us at the moment. So hopefully this has been helpful and kind of giving you an idea of what these sets tend to look like. And this is going to kind of come into play when we introduce a theorem that works with finding minimums and maximums for functions later. So just so you have an idea of how this all fits in. But anyway, thanks for watching, and I'll see you next time.